So, welcome to this lecture in module 2. In this lecture, we will be discussing the effective current for near threshold voltage combinational gates, inverter and NAND gate essentially. So, we will first discuss the effective current model for an NTV inverter. So, in this we have already derived a value for the input voltage value when the output starts to discharge. Okay. So, we will begin from that point and we will discuss the effective current model for an inverter, in near threshold voltage inverter. Thereafter, we will discuss the near threshold voltage NAND gate, 2 input NAND gate. So, we will derive an effective current model for the 2 input NAND gate. So, we had divided the output discharge into 2 parts. One was from the point when the output voltage is at its peak, and from there to when the output voltage goes to 0.8 VDD. So, what is the current between these two? So, we observed that the current between these two is increasing linearly. Okay. So, and thereafter it stays constant, we will discuss the reasons for that. So, for to obtain an average discharging current between these 2 points, it is very simple because it is a linear increase and you can work with an average discharging current and estimate the time period elapsed between these 2 points, that is when the output voltage is at its peak and when it goes to 0.8 VDD. So, between these two, whatever is the average discharging current, that will determine the duration from here till here. Okay. So, why do we want this value? So, we will first what we are doing is that we are estimating the time at which this peak happens, and at that time what really we want is what is the input voltage at that time. So, once we get the input voltage value at that time, so we know the input voltage value, we know the output voltage which is the peak, which is nearly VDD. So, we know both the terminal voltages, all the terminal voltages for this transistor N MOSFET, and we can therefore calculate its current at this instance. So, that is when at the point when the output is at its peak value. So, we get the value of current at this point and then we will get the value of current at this when the output voltage is 0.8 volts, and we take an average that will give us the discharging current in this duration, and then we will also then will thereafter discuss the discharging current from the time when output is 0.8 VDD to the time when output is VDD by 2. So, that is how we will estimate the time durations between different instances of output voltage, and that will adding up all these we will get the delay value, and we will relate this to effective discharging current, and that effective discharging current would depend on DC terminal voltages. So, it is very easy to extract for a given PDK this effective discharging current, and once you extract that you can relate it to several parameters, variability parameters. For example, if threshold voltage changes by a certain value, how much does the effective discharging current change, that we can estimate, or if the supply voltage changes by a certain value, how much does the effective discharging current change, that we can estimate. So, that way that gives us a good handle to consider variability in circuit design. So, this we had in the previous lecture we had discussed how we obtain this value of V in C, which is the value of the input voltage when the output voltage is at its peak, and this is given by this simple expression. So, what could be the reason for this output current to increase linearly from this point to this point? So, this is actually, if you look at the current expression between these points, or if we write the KCL at this output node between these points, how would you write it? You would say that the current is I naught exponential, the output voltage value is, so what is the gate voltage? Gate voltage is VDD T by TR, if we consider the input voltage to be rising almost linearly. This is Vg minus VTH, VTHN, okay, plus DIBL factor lambda V out, okay, divided by NVT. We can neglect the VDS term. That is because VDS is much larger than the thermal voltage, and therefore, we can neglect the second term which multiplies into this. Okay. So, this is the output current. So, you can see this is equal to this is the current entering the output node from the input node. This is the current going out of the output node. So, now what you observe is that this is a constant in case. So, this is a constant because we are observing, we are considering the input voltage to be rising almost linearly. So, this is a differential equation where you can also see that the output almost falls linearly. So, this is a differential equation where the value of the current would have to increase linearly with time. So, would have to increase exponentially with time. So, there is an exponential relationship, and because the time constant here would be quite large compared to the time durations with which we are dealing, this exponential relationship turns out to be linear. That one can show by using the values obtained from simulation. You can take this almost linear fall of the output voltage here and see that the exponential function for the output current is such that the time constant is much larger than the duration that we are dealing with, and therefore, there is almost a linear kind of increase in the current. Okay. And because of the one-to-one relationship between the input and output terminal voltages which we had discussed earlier, you would observe that this V in C is fairly constant for a change in fan out. So, fan out load is keeping changing in the inverter chain, stage fan out load. It is balanced inverter chain with equal fan out load for each stage, and you observe that this V in C, this is the V in C value, and V in C is almost constant for two different PDKs or two different technologies. One is a PDK at 65 nanometer node, and the other one is a TCAD simulation of a typical 32 nanometer node. So, for both of them you observe that with fan changing fan out, the value of V in C is almost constant. So, that is because of the one-to-one relationship between input and output. So, that V in C, though we can calculate it as we had shown earlier, it is almost this much. Why is the expression that we had derived for V in C earlier important? That is important because if you want to consider variability, say change in VDD, change in threshold voltage, change in the coupling capacitance between input and output nodes. So, these you can include very easily and obtain the changed value of V in C with respect to variability. So, what is the average discharging current? So, it is the current IL at this point and IH at this point when V out is 0.8 VDD, okay, and the average of these two is the average discharging current from V in C, V in is equal to V in C to V out is equal to 0.8 VDD between those two times. Okay. Now, we want to obtain the average discharging current between the values of output voltage from 0.8 to 0.5 VDD. So, between these two we want to now find out the average discharging current. So, these are simulation results of 65 nanometer node. So, what you can observe is that this is the value of V in C, as we had discussed, it is near 75% VDD, and this is the value at which V out is 0.8 VDD. So, what is the value of V in here? That is this, and you want to estimate the current from this V out being 0.8 VDD to V out being 0.5 VDD. So, between these two you can observe that the current is almost constant. That you can also see here that for different fan outs, what we have done is we are seeing the current from 0.8 VDD to 0.5 VDD, and you can see that it is fairly constant for different fan outs. What is the reason? So, here the input voltage is increasing between these 2 points. So, here you are 0.8 VDD and this is 0.5 VDD. The input voltage is, you can observe that the input voltage is rising quite slowly. Input voltage is increasing quite slowly, output voltage is falling rapidly. Okay. And we know that output discharging current is given by exponential V in minus VTHN minus lambda plus lambda V out by NVT. Okay. Now, V in is between these two values, V in is slowly rising and V out is rapidly falling. So, V out is rapidly falling because see the current is significant. So, V out is rapidly falling, V in is slowly rising. So, the reason for slow rise of V in is that this X3 is being driven by X2 and X3 is this inverter under device under test. So, its output is falling, and because of back coupling from this coupling capacitance, though X2 is driving the input of X3 high, there is, because of this back coupling, this is falling rapidly, this voltage. So, because of the coupling capacitance, what we observe is that the rise of X2 is also very slow. So, that is because of the coupling capacitance Cm. And in near threshold circuits, the drive currents are not very high, and that too at this limit when the input is rising, the P MOSFET of X2, which is causing this rise of the input of X3, is already in linear regime. It is in linear regime, and therefore, the current through it is quite small. The P MOSFET of X2, the drive capability is quite small, and the back coupling from Cm starts dominating, and the output rise becomes quite slow here. So, the inputs rise. So, output of X2's rise, okay, that is input of X3, it is rising quite slowly. Since this is input is rising slowly and output is falling rapidly, and lambda is smaller than 1, this is DABL factor, it is quite small compared to 1. So, therefore, you find that these two almost cancel out each other and the current is almost constant, as can be seen here between these 2 points, V out being 0.8 VDD and V out being 0.5 VDD, it is almost constant. Okay. For different fan out loads also you can see the same. So, we want to now estimate this value of current. So, what is the value of this current? IH, we call it IH. It is for gate voltage being 0.95 VDD, drain voltage 0.5 VDD, okay. It is almost constant here, and source and body voltage and the source voltage being 0, okay. And what is IL? IL is the current when V in is V in C, and it is for Vg being V in C, Vd being this thing VDD, because Vd is almost VDD here, and Vs and Vb being 0. So, now what is V in C? V in C we have already calculated in the previous lecture. So, we can obtain the average current between these two values, these 2 points, and we can obtain the current here. This is a constant. So, we can estimate the discharging time from V out being Vp to V out being 0.5 VDD, okay, that we can estimate. So, let us divide this entire thing into 3 parts. So, the input voltage is 0.5 VDD. What is the delay? Delay definition that we are using, it is a 50% delay. So, input voltage is 0.5 VDD to what is the time that is elapsed when the output voltage is 0.5 VDD. So, between these two, the time duration we call it delay. Okay. So, now we have a way to estimate the time duration between these 2 points and between these 2 points, as we had discussed earlier. but how do we find out the time duration between these 2 points? That would be a topic of discussion later. First we will just calculate the time duration between these 2 points, that is when V out is Vp to V out is 0.5 VDD. So, from the point where time when V out is Vp to V out is 0.8 VDD, the value of average current we said that the average current is this IL plus IH by 2, isn't it, because it is almost a linear increasing current. Okay. So, what is the time duration corresponding to this? So, this discharge is, so let us call that time duration as T1, and the T1 would be, so the discharge is from VDD to 0.8 VDD, isn't it? So, VDD minus 0.8 VDD into load capacitance or total output capacitance, which is the charge. So, this is the charge and that is being discharged by IL plus IH by 2. Okay. So, this is the time duration T1. So, this we are calling T1, okay, and this is the 50% value, this we are calling T2, we will estimate that later. So, from V out going from 0.8 VDD to 0.5 VDD, that is this time T2, this what is the time duration T2, it is 0.8 minus 0.5 VDD into CL divided by almost a constant current is there. So, it is IH. Okay. So, we add these two. IH plus 0.3 VDD-CL by IH. Thereafter, we want to obtain the time duration delta T, we call this delta T, between the points when the input voltage is 0.5 VDD to the point when output voltage is Vp. Okay. That is when input voltage is V in C. So, that we add to this T1 plus T2 to obtain the total delay. So, to obtain the value of delta T, which is this we are calling delta T, to obtain the value of this delta T, we make the following observations. The input and output transition times are almost equal, and this is quite more valid near the 50% points of input and output. The input and output transition times are equal. So, how do we obtain this? If we know what is this discharge, so we know that V in C is a certain fraction of VDD. So, V in C minus and it is almost constant with respect to change in fan out. Okay. So, V in C minus VDD by 2, whatever fraction that is of the total transition, an equal transition at the output would take the same amount of time. So, because input and output transition times are matched in our case. So, therefore, for input to rise from VDD by 2 to V in C, if we see an equal amount of fall in the output, both should take the same time. Okay. So, we estimate the latter, that is whatever is the magnitude of change from input changing from VDD by 2 to V in C, the same magnitude of change of output voltage, how long does it take? That is what we will estimate, and we equate both of them and thereby estimate this delta T, and then add it to T1 and T2 to obtain the total delay. So, what is the fraction? V in C minus VDD by 2 divided by VDD. This is the fraction of change in input voltage, total transition. Total transition is VDD for the input voltage, and this is the fraction. So, this is nearly, if V in C is 0.75 VDD, this is nearly 0.25 VDD. This fraction is nearly 0.25. So, the output discharge for a 0.25 for 1/4 of the output transition, what is the time that is taken near the 50% point. So, I would, what we would be doing, we would say that delta T is equal to CL into 0.25 VDD divided by I out, and output voltage when V out is 0.5 VDD. So, at this in this region, whatever is the output current, so what time does that current take to discharge the output node by 1/4 of the overall transition. Okay. So, this is the charge, amount of discharge, and output current when V out is equal to 0.5 VDD. So, now we add all these terms. So, delay of the inverter is T1 plus T2 plus delta T. So, that is 0.4 CL VDD by IL plus IH plus 0.3 CL VDD by IH plus 0.25, this is delta T as we have obtained, CL VDD by IH, because the current I out when V out is 0.5 VDD is IH, as we had discussed earlier. So, this when added becomes CL VDD into 0.95 IH plus 0.55 IL divided by IL plus IH into IH. Now, this we equate to CL VDD by 2, this is the discharge for 50 divided by I effective. Okay. So, CL VDD by 2 because you are dealing with 50% discharge divided by effective switching current. So, if you substitute this, you get I effective to be IH into IL plus IH divided by 1.9 IH plus 1.1 IL. Okay. Now, how is this useful? What is the value of logical effort? So, we can look at logical effort as being the ratio of capacitances and currents of the gate for which we are estimating logical effort to the reference inverter. So, we can write it down as our inverters C in divided by reference inverters C in into reference inverters I effective divided by our inverters I effective. How could they both be different? Suppose the reference inverter has a certain finger width, and now for our inverter you change the finger width. Okay. So, then you have a different value of threshold voltage because of the change in inverse narrow width effect. So, that would give us a different I effective, and Because we know that with width how the threshold voltage changes due to inverse narrow width effect, we can estimate with width how the logical effort of an inverter would change with respect to a reference inverter with a certain layout. So, with this we have obtained an effective current model for subthreshold or near threshold inverter, which can be used to estimate the value of effective current when with changes in layout, with changes in temperature, with changes in supply voltage or mobility, etc. Because this effective current model is based on two DC current values with a certain terminal voltages. So, this is an effective current model which can be used or consider variability in the circuit design itself. Thank you.